We continue the geometric modeling course. This lecture is also related to the course topic on modeling curves and surfaces. The theme of this lecture is devoted to shapes defined with a point classification rule, so-called implicit curves, surfaces, and solids. The structure of this lecture is following. First, we recall the use of point membership rules to define point sets. Then we give several examples of implicit curves. Types of implicit surfaces and corresponding solids will be covered in more detail. They are algebraic, skeletal, and convolution implicit surfaces. As we have already discussed, one of the ways to define a shape or a point set is to have a point membership rule in the form of a black box, where we input a point and the box gives us one of two possible answers. Yes, this point belongs to the shape, or no, this point is outside of the shape. The binary yes and no information is enough to unambiguously specify any point set. However, this information is quite limited for practical dealing with such objects in numerical algorithms. It would be much better to have a real valued measure of the distance of the given point to the object boundary. Such an extended black box is used for implicit curves, surfaces, and solids. If we take some real continuous function of point coordinates x and y on a two-dimensional plane, and then select all the points on the plane where this function has zero value, the collection of points we found is called an implicit curve. If we change the equation to an inequality, we define a two-dimensional area, a piece of plane or two-dimensional solid or a planar area, and the implicit curve will be its boundary. This all can be understood much easier with a practical example. With a simple function shown above, the point membership rule is the equation f equals 0 that defines a circle as an implicit curve, which is a one-dimensional shape in two-dimensional space. Note that the function is written in such a way that it has positive values inside the circle and negative outside. If we change the equation into an equality, we define the circle and all the points inside. This object is called a disk, which is a two-dimensional area or a two-dimensional solid. This principle is the same for all types of function and dimensions. The defining function is positive inside the shape, negative outside, and has zero value on the boundary. An ellipse can be thought as a disk stretched and squeezed in different directions. It's another representative of so-called quadratic curves defined by polynomial functions of degree 2. The shown equation has two parameters a and b, which are lengths of half-axes along x and y directions correspondingly. A superellipse has a very similar equation, but the power 2 is changed to the power n. With n greater than 1 left image, the shape is close to a box. With n lesser than 1, it looks like a star with sharp ends. This is a representative of algebraic curves defined by polynomial functions of any degree. There is a great variety of algebraic implicit curves. They are studied in analytic geometry. Let me show you just one more but very popular curve. The Lemniscate was first described in 1694 by Jacob Bernoulli as a modification of an ellipse in the implicit form. It is described by the polynomial of degree 4. The curve has become a symbol of infinity and is widely used in mathematics. Let us make a step one dimension higher from implicit curves to implicit surfaces. Consider a continuous function f of point coordinates in three-dimensional space. The equation f equals 0 defines a so-called implicit surface, which is a two-dimensional shape in three-dimensional space. There is a question on whether the term implicit is correct. We will consider it further. To understand the origin of the term implicit, let us briefly recall school mathematics. There are two ways to define variable z as a function of two variables x and y. It is explicit form and implicit form. In both forms, one pair of x and y coordinates corresponds to one and only one value of z coordinate. Therefore, both forms are not enough to define even a full sphere, only a hemisphere. Let us now introduce variable x as an explicit function of three variables. A surface where x takes zero value is an iso-valued surface, or simply an isosurface of an explicit function of three variables. Note that the expression looks exactly the same as the implicit form from the previous slide, but the meaning is completely different. So, such a surface is called an implicit surface as the historical accident, not for mathematical reasons. Due to explain the situation, let me propose the following rule. We can use the slang term implicit surface, but not implicit function, because it is simply incorrect. The functions we are dealing with are called defining functions. The inequality f greater or equal 0 defines a three-dimensional solid, and the zero value is the surface or implicit surface, is its boundary. There are several classes of implicit surfaces depending on the type of their defining functions. They are algebraic surfaces, skeletal implicit surfaces, and convolution surfaces. Surfaces with polynomial functions are called algebraic surfaces. For the polynomials of degree 2, these surfaces are called quadratic. Well-known quadratic surfaces are sphere, ellipsoid, cylinder, cone, paraboloid, and others. Widely used in computer graphic surfaces with high degree polynomials are torus and superellipsoids. Let's consider algebraic surfaces in more detail. Symmetrical to the two-dimensional case of a circle, the shown equation defines an implicit surface called a sphere, and the inequality defines the sphere and all the points inside, making an object called a solid ball, or simply a ball. An ellipsoid can be thought as a sphere, stretched and squeezed in different directions. The shown equation has three parameters, a, b, and c, which are lengths of half-axes along x, y, and z directions correspondingly. When these parameters are equal to each other, we get a sphere, as a particular case. A torus, or a denote, is a shape swept by a small disk rotated around an axis, parallel to its plane. In fact, it is defined by a polynomial of degree 4, but here it is shown in a specific form with a square root. The equation has two parameters. Small r0 is a radius of a small disk, and the big R is a radius of rotation, which is usually greater than radius of small disk. Superellipsoids are popular in computer graphics because by changing just two positive parameters S1 and S2 in the given formula, one can get a variety of different shapes. For both S1 and S2 equal 1, the equation defines an ellipsoid. When both parameters are less than 1, we get a shape close to a box in the upper left corner of the image. For S1 and S2 greater than 1, it is a star shape in the lower right corner. Algebraic surfaces can be very complex depending on the degree and type of polynomial function. The shown surface is defined by a Chebyshev polynomial of degree 6 and has a record number of critical points for algebraic surfaces of this degree. In a critical point, the surface is reduced just to a single point, and we see many of them in this surface. The idea of skeletal implicit surfaces was brought to computer graphics from physics. Imagine a point in space with a source of some scalar field, for example, temperature. Such a point is called a field source or a skeleton point. In the blobby model proposed by Blin in 1982, an electron density field was used by analogy. The surface of the equal field value for the given threshold is a sphere, as shown in the image. Different values or levels correspond to different spheres. There can be many skeletal points or other geometric shapes as skeletons placed in space. In the definition of skeletal implicit surface, there are the following model elements. Skeleton consisted of skeletal points, lines, and others. Scalar field with an individual skeleton element as a source. Global field as an algebraic sum of individual fields. Level or threshold of the field value defining the isosurface of interest. When we put several field sources in space, the surfaces of the constant field value become smoothly blended spheres, as it's shown in two-dimensional example at the left and in the three-dimensional example at the right. Note that just 6 skeletal points make a quite complex surface. The definition of the skeletal implicit surface includes the following items. The global scalar field f of p, which is an algebraic sum of individual scalar fields depending on the distance to a skeletal element. N is the number of skeletal elements. T is the level value we select for the global field. C is weight. It can be positive or negative. Depending on the type of the individual field, there are blobby model, metaballs, and soft objects. Blin, in his blobby model, used the shown formula with the exponential function for the individual scalar field of a skeletal point. The plot of such the scalar field in the blobby model is shown here. It is a function of the distance from a given point to the skeleton point. Distance 0 means the skeleton point and the field is maximal at this point. Then, the field is decreasing with the distance from a skeleton point. The problem with this function is that it never becomes zero, meaning that each skeleton point has global influence on the shape at any point in space. There are several models fixing the problem of the global influence. The idea is to make a scalar field which drops to zero at the given distance from the skeleton point and does it tangentially to the horizontal axis. The first model of this type was proposed in Japan and is called metaballs. The given value d in the expressions is called the radius of influence, meaning that there is no scalar field of this point beyond this radius. The formulation uses two quadratic polynomials nicely tailored together at the distance of 1/3 of d. Soft objects use one polynomial of degree 6 to achieve the same goal of getting zero scalar field at the given radius of influence. Note that the shapes of blobby, metaballs, and soft objects are similar. It is just easier to control the surfaces with a localized scalar field. If look closely at the skeletal surface definition, it is practically independent of the type of skeletal element. There is a parameter of distance to the skeletal element. Therefore, if such a distance can be provided for another shape rather than just a point, this shape can become a skeletal element. That's why practical modeling systems usually include some of the following skeletal elements: straight line segment, parametric curve, polygon, and even parametric surface, which requires computationally expensive numerical distance calculation. The major problem with including new skeletal elements is that it often results in unwanted bulges in the surface at the places of their intersection. This is a soft object strain model by Brian Wewell and co-authors. You can see all the individual elements in the left image and then they are blended together in the right image. This is animation called soft by the authors of soft objects. Note how the motion of shapes is controlled by moving individual skeletal points. In convolution surfaces, the skeleton elements are not only points, but line segments, arcs, and other curves and surfaces. We can think of such a skeleton element as a set of points with distances between them becoming infinitely small. In this case, an algebraic sum used in skeleton implicit surfaces turns into the shown integral of a scalar field or kernel over the skeleton. In the shown definition of the convolution integral, S of x is a predicate function defining geometry of the skeletal element. It takes value 0 for points not belonging to the skeleton and value 1 at the skeleton. H of x is a convolution kernel. Usually such integration means heavy numerical calculations. Superposition of convolutions is a remarkable property which helps completely avoid unwanted bulges appearing in traditional skeletal implicit surfaces. The shown expression means that integration over the entire skeleton with two skeletal elements, shown at the left part of the expression, can be replaced by integration over each element separately, and then the results are added by algebraic summation as shown at the right part of the expression. As we mentioned, numerical integration usually requires heavy computations. However, with a good choice of skeleton elements and a kernel function as shown on this slide, one can get analytical formulation for convolution surfaces, as it was done by Shrestuk in 1998. He derived analytical expressions for the following skeletal elements of convolution surfaces: point with the kernel itself as a scalar field, segment, circular arc, triangle, and a plane. These elements made a good toolset for modeling quite complex convolution surfaces. These two slides show examples of objects modeled with convolution surfaces only. The skeletal elements are segments, circular arcs, and triangle meshes. As you can observe, the seahorse model is practically constructed of only circle arcs with convolutions around them. The seashell model is opposite. Its shape is defined by a triangle mesh smoothed by a convolution surface. Why skeletal implicit surfaces are so popular in computer graphics? They are intuitive representation for natural objects such as molecular shapes, liquid and melting objects, animal and human body. They provide automatic shape blending. Skeletons are easily manipulated and displayed. It's very useful in making animations. You operate with the skeleton only, and the surfaces follow the skeleton motion. Skeleton surfaces have more concise representations than parametric surfaces. The above models made with parametric surfaces would require much more memory to store and much more time to make. Complex shapes can be modeled with few primitive elements, especially with convolutions. It's easy to add new primitive types to blobby or metaballs. You only need to define a new skeleton or a new field function. However, it's not easy to extend the set of convolution surface primitives, because it needs integration in the analytical form. This is our main textbook where several chapters deal with geometric modeling. These are the reference book on implicit surfaces and two major references to convolution surfaces.